Welcome to our fifth lesson on acids and bases. In this lesson, we're going to be taking a look at our Kw, which is going to stand for our ionization constant of water, and some of our pH calculations. Now let's start off by taking a look at the ionization of water. Remember, ionization basically means the breaking up into smaller particles here. Now, do take into account that water is an amphibole, as we've discussed in some of our previous lessons. Now, let's take a look at a reaction that will actually show how water is an amphibole with itself. If we would have two water molecules reacting with each other, then one of these water molecules is going to act like an acid, and the other one will act like a base. That means the one that's going to be donating our hydrogen ion is going to act like the acid, and the one that's going to be accepting it is going to act like the base. Now, once it has indeed ended up donating a hydrogen ion, it will become an hydroxide ion. And once it has accepted this hydrogen ion, it's going to become the hydronium ion. Now, referring again to our conjugate acids and bases, obviously the one that have donated the hydrogen ion is going to end up being the hydroxide ion. So this is going to be then acid 1, and that will be with base 1 or the conjugate base. If you go back again to our first one, which has accepted the hydrogen ion, this will be base 2, and it will become the hydronium ion, which will then be called our acid 2 or our conjugate acid. So we can see in this reaction, water is acting as both an acid and a base, and is therefore seen as an amphibole. Now, this is a reversible reaction. In the beginning, I've indicated that the arrows going forward and backwards is exactly the same size. But in this specific reaction, it's actually not the case. Water would far more like to be in the water molecule form than ending up breaking up into its constituent ions. Therefore, my equilibrium lies more towards my left-hand side, and we'll have a smaller arrow then pointing towards the right-hand side. Now let's go and apply this to my Kw. Now Kw stands for the ionization constant for water. So immediately it tells you it's a constant value, will always be the same, and we then indicated this with a W. K is usually standing for constant, and W stands for the fact that it's for water. Now this can also be called the ionic product of water, but it means exactly the same as the ionization constant for water. Now remember, just like you had in your chemical equilibrium constant Kc, this ionization constant is serving the same type of purpose. And we can go and write down this equilibrium constant for water as being Kw equal to, and in this case, the concentration of the hydronium ions multiply the concentration of the hydroxide ions. Now you might wonder, how come that is actually going to be our ionization constant for water? Remember when we take a look at our Kc, which was the equilibrium constant, we said that that was equal to the concentration of products over the concentration of reactants. But the only things that was allowed to be used as concentration of products and reactants in this Kc expression were aqueous solutions as well as gases. Our pure liquids and our solids were not included in this Kc expression. Now let's quickly go back again to that water equation where we've realized that water is an amphibole when reacting with itself. Now when we take a look at the phases, pure water is seen as a liquid. So when it's in its H2O molecular form, it's a pure liquid, but the moment that it breaks up into ions, then it will always be an aqueous solution. So remember, whenever things is in the ionic form, we see them as an aqueous solution. So the same situation is applying here. We want to go and write down our Kw expression by saying concentration of products over reactants. So our products is going to be the OH minus and the H3O plus. Our reactants would have been water, but because it's a pure liquid form, it's not included in the expression. That's how come we only write down the products, and that's at the top of the line, which in this case is the hydroxide ion concentration, multiply the hydronium ion concentration. Now, usually we went and calculated your equilibrium constant value. Now, your ionization constant for water is always going to be given to you. You would never need to calculate that value, seeing that it's a constant when we've got pure water. Now, this constant value is 1 times 10 to the power of negative 14. That means whenever we are going to multiply the concentration of the hydronium ion with the concentration of the hydroxide ion, we should always end up back again with 1 times 10 to the power of negative 14. So should it happen maybe that you've got a high concentration of H3O+, you'll have a lower concentration of the hydroxide ion in order to end up again with 1 times 10 to the power of negative 14. Now let's say you've got, in this case, a neutral solution. And neutral basically would refer to us that the pH is going to be around about 7. But before we get to the pH, let's just talk about a neutral solution. In a neutral solution, our concentration of the hydronium ions will be equal to the concentration of the hydroxide ions. And just to clarify again, remember hydronium ions is responsible for the acidic properties of an acid, and the hydroxide ions is responsible for the basic properties of a base or an alkaline. So if these concentrations that's responsible for acids and bases is equal, then it means we've got a neutral solution. Now, that would mean that each one of them would end up having individually a concentration of 1 times 10 to the power of negative 7 mole per cubic decimeter. And we can easily get to that, seeing that we said the concentration of the hydronium ion, let's make it X, is equal to the concentration of the hydroxide if it's neutral. So it actually becomes X times X, which is X squared. So X squared is equal to 1 times 10 to the power negative 14. But if I want to have X alone, then I'll do the square root of 1 times 10 to the power negative 14. And that gives me 1 times 10 to the power of negative 7 mole per cubic decimeters. So you can go and memorize the following. The fact that your Kw, which is the ionization constant for water, is always 1 times 10 to the power of negative 14. That's equal to the concentration of the hydronium ion, multiply the concentration of the hydroxide ion, and for a neutral solution, it would mean that this hydronium ion is equal to the hydroxide ion, and that will then be this constant concentration of 1 times 10 to the power of negative 7 mole per cubic decimeter for each one of them individually. Now let's go over to our pH scale. Our pH scale's value ranges from 0 up until 14. Now I'm sure from your grade 8 and 9 knowledge, you've realized that if your pH lies then below 7, that basically means from 0 up till 7, we will have an acidic solution. If your pH, on the other hand, would lie higher than 7, and in our case, if you take a look, that means from 7 up until 14, then you'll have a basic solution or an alkaline solution. Remember, we call a base that is able to dissolve in water an alkaline. If you should end up with a pH equal to 7, then it refers for us as a neutral solution. Now, when calculating the pH, there's a specific formula that we make use of. This formula will be given to you, and that's equal to negative log multiply the concentration of the hydronium ion. Not the hydroxide ion, not water, but the hydronium ion concentration. This is the formula for calculating pH. You will also note that sometimes they give you the hydrogen ion concentration, and that's exactly the same thing as the hydronium ion. So whether they talk about the hydronium ion or the hydrogen ion, that means exactly the same thing. So your pH is measured in the relativity of your hydronium ion concentration. Now let's quickly go back again talking about acidic and basic solutions and when it's neutral. So once again, if you've got a neutral solution, that means a pH of 7. We've said earlier on that Our hydroxide ion concentration will be equal to the hydronium ion concentration, and we said that that value for the concentration will be 1 times 10 to the power negative 7 mole per cubic decimeter. So that means, seeing that I want to go and calculate my pH, and I'll need the hydronium ion concentration only, for a neutral solution, you will always have your hydronium ion concentration equal to 1 times 10 to the power of negative 7 mole per cubic decimeter. So I suggest you go and punch it into your calculator using negative log, and then you put in 1 times 10 to the power of negative 7, and you realize you end up with a pH then of 7. Now, if you have an acidic solution, it means your pH is less than 7. And that would happen when your hydronium ion concentration now obviously is not equal to 1 times 10 to the power negative 7 anymore, but it will be greater than 1 times 10 to the power of negative 7 mole per cubic decimeter. So if your concentration of the hydronium ion, which indicates the acidic properties, is higher than the neutral value, it will make it an acidic solution which has a pH of less than 7. Now the opposite would be true for your alkaline solution. Now we'll be talking about a pH that will be greater than 7. And that means my hydronium ions, which remember is responsible for the acidic properties, will be less than 1 times 10 to the power of negative 7, because our solution is now more basic than what it is acidic. So there's less of my acidic ions present and more basic ions, therefore it's less than 1 times 10 to the power of negative 7.